Hello and warm welcome to today's video where we will be going through 9 of the latest questions from aircraft general knowledge, all of course AGK. All these questions that we'll go through today have been seen and marked as recent in the actual real ATPL EASA exams. So without any further ado, let's just jump into these questions and I'll try to give you as much extra tips and information as well as the explanations. So for question number 1, consider a turbine engine airplane with 2 underwing engines fitted with 2 wing tanks and 1 center tank. If all center tank booster pumps fail, what happens? And of course, this architecture it will be found in most airliners where we have at least 2 booster pumps fitted for each of the fuel tanks, the left wing tank, the center tank, and the right wing tank. And of course, what happens if one of these fails? As an example, I can give you the Airbus A320 family, where the center tanks, they actually cannot gravity feed, for example, and this is only possible through the wing tanks, which will give you some of the fuel, but not all of it, because of course the drains are not fitted at the bottom of the tank to allow for some residue to settle down, but slightly higher. This means that some or all of the fuel from the center tank, in this case all of the fuel, but in some engines some of the fuel will need to be considered unusable for the duration of the flight. This will also have some other implications on the maximum altitudes that can be flown. However, this question can be considered type specific. Generally speaking though, the center tank will not gravity feed, only the wing tanks can gravity feed, and some of this, and because of this, most of the center tank fuel needs to be considered unusable, and even if not, then some of it will always be unusable, including the fuel in the wing tanks. You will never use all of the fuel using gravity feeding only, meaning part or all of the fuel is considered unusable. For question number 2, with respect to a piston engine aircraft, ice in the carburetor will form. And of course, this is also a question that is very often asked during the flight phases of the training as well, not only during the ATPL exams. A carburetor simply creates a mixture of fuel from the atomizers and air that is then sent into the combustion chamber of the pistons. The carburetor works using the Venturi principle. There is a butterfly valve or the throttle valve that opens and closes as you add more power to the engine. This of course creates the Venturi effect, and the increasing and the dropping static pressure decreases the temperature, creating some icing. This is why all carburetors are fitted with carburetor heating in order to prevent this, as well as the atomization of the fuel that is coming out of the atomizers also supports the creation of icing. It is very important to remember that because of this, icing in a carburetor can happen well above temperatures of 0 degrees, and this is because of this drop of static pressure inside of the carburetor. Of course, you should remember that the supercooled water droplets in the air, so the liquid water will be in the air anywhere from 0 to -15, in reality even lower than that, -40 degrees. However, when it comes to carburetor icing, it can absolutely form at temperatures above 10 degrees, and this is due to what we just discussed. The dropping static pressure in the carburetor decreases the temperature dramatically during the passage of the air through the Venturi. For question number 3, which of these statements concerning oxygen on board passenger transport airplanes is correct? So a few things that I just wanted to remind you about the oxygen systems, as these come up on all AGK exams, is that remember that every commercial aircraft needs to be fitted with some form of oxygen systems. The oxygen systems will need to provide at least one extra oxygen mask per a seat of row. So if there is 3 seats, it needs to give you 4. This is for the passing cabin crew. There also needs to be oxygen. Needs to be an oxygen in the lavatories for people who are in the lavatory during the pressurization, and also the cabin crew will have oxygen that they can pass through the cabin with. Remember that the oxygen is by law mandated. The oxygen masks, they need to drop automatically if the cabin altitude reaches and exceeds 15,000 feet. On some aircraft it will be lower, but generally for the exams 15,000 is the right mark. And in the cabin altitude cannot be higher than 8,000 feet. So going back to the question, of course, remember also that there are 2 systems: the chemical system, which creates a chemical reaction that is a byproduct of the burning, creates oxygen. This will last approximately 15 minutes, and remember that once it starts, it can never be stopped. And then there are also general oxygen systems, that are using the centralized system for on the Boeing 747 or 777, for example, and these will be centralized and they work in a slightly different way. Simply, we have oxygen tanks in the aircraft. So going back to the questions, of course, since lavatories are not fitted, that's not true. They are. Chemical oxygen generator lasts for 15 minutes, not 1 hour. After being activated, a chemical oxygen generator does not produce any heat. It will produce a lot of heat because it's a burning reaction that as a byproduct produces oxygen. And portable oxygen bottles in the cabin are primarily intended for first aid purposes, and absolutely that will be the correct answer. Question number 4. Why do large jet engines need a spool-up time? And the spool-up in these turbine engines is a quite a straightforward reaction. The spool-up time is essentially time that the FADEX, if you add a lot of thrust for your engines, the FADEX will limit the fuel flow initially, because if there is too much fuel at once added to the turbine engine, the engines will simply stall. This is because the pressure that will be created inside of the combustion chamber will be too much. And what will happen, the air moving from the front to the back of the engine will move too fast, and essentially it will detach the airflow from the turbine blades and the compressor blades, essentially stalling the engine inside. This is why the FADEX will limit the fuel as you add the oxygen at the approximate rate, so that the fans can spool up and increase the speed accordingly, so that then when we have a lot of thrust added, the air is not stalling on top of these fans, and it can go smoothly throughout the entire engine. So of course, this will be the reason why the engines need a spool-up time, and also why the engine startup takes significant time, relatively speaking, around 1 to 1 minute 20 seconds, rather than instantly like with the propeller engines, for example. And of course, making the correct question a requested for rapid acceleration may cause a flame out due to overly rich mixture. And I will say no, the overly rich mixture doesn't make much sense, because the engines are controlled by the Electronic Engine Control Unit, ECU. The calculations required to meter the correct amount of fuel produce a delay, also no. And of course, this will be this one. Of course, we do not talk about mixture when it comes to the turbine engines. The fuel is added into the exhaust chamber. However, yes, this is in order to limit the pressure gradient inside of the engine. For question number 5. During level cruising flight, an airplane experiences a malfunction of the pressure controller. If the cabin vertical speed indicator reads 200-minute rate of descent, what happens inside of the aircraft? So of course, if inside of your cabin you have a rate of descent, this means that your cabin altitude is dropping, which means that the pressure is increasing. With the increasing pressure inside of your aircraft, what happens is that the main danger is that delta P, or the differential pressure between the inside and the outside of the aircraft. This should approximately be at the value of 7 psi. This of course will depend directly on the specific aircraft and the manufacturer. However, this delta P cannot exceed the maximum limit. So if you exceed this limit, what will happen is that the relief valves in your aircraft will start opening in order to maintain the delta P at the maximum and no more, because otherwise the aircraft will simply be crushed and destroyed immediately, because the pressure and the structure cannot maintain these forces on the aircraft itself. So of course the differential pressure, so between inside and outside of the aircraft, will rise to the maximum initially, and then the safety relief valves will open and keep it at that maximum limit and no more. Question number 6. Which one of the following is an advantage of a high-pressure hydraulic system over a low-pressure hydraulic system? So remember that new and modern airliners will have the pressurized systems, the hydraulic systems pressurized at approximately 2, most cases 3000 psi. Some aircraft like the A380, for example, they have a high-pressure hydraulic system which goes to up to 5000 psi. This of course allows to have the system transfer greater loads, so the system is more capable. However, this comes at increased costs, maintenance. Of course, the parts are being exposed to bigger stresses, so of course this system will be much more sophisticated, much more expensive to maintain, and this is also why most manufacturers they settle down at this 3000 psi mark. So of course, going here to the answers, a high pressure system is able to handle greater loads than a low pressure system. However, it means higher maintenance costs, higher operating costs, and more strain on the aircraft parts. Question number 7. After air has passed through the compressor of a gas turbine engine, what will happen inside? And of course, as the air passes through the compressor, then of course the air is getting compressed, the density of the air increases, and the temperature rises as a byproduct of this. And the temperature, of course, rises relatively slowly, and then it rapidly as you reach the exhaust chamber. Then, of course, it drops and the energy is released as a thrust behind the engine. Question number 8. The function of a fusible plug is to. A fusible plug is something that is inside of the wheels of your aircraft, and this is a very simple design that has prevented many disasters in the past, and of course it does on the daily basis. A fusible plug principle is very simple. Essentially, it's a plug inside of your wheels that has a melting point slightly below the melting point of your tires. In effect, if the tires, for example, because of rapid braking, are heated to extreme temperatures, the first thing that melts is not the tire, which would cause an explosion, but a fusible plug, which is designed to do so, and then it releases all the air from the tire in a controlled manner rather than an explosion. And of course, if this one is not the case, then the tires will be bursting, which can cause harm to the aircraft or people around it. So of course, they will protect the tire against the explosion due to excessive temperature because the fusible plug melts, and then, of course, the air can escape in a controlled manner. A multi-engine piston aircraft, both the propellers rotate clockwise as seen from the cockpit. In a go-around, one of the engine fails. Which of the following situations will most probably need the pilot to use full rudder deflection? And of course, we're talking about the critical engine failing and the most adverse conditions. So remember that when we have clockwise turning propellers, the thrust vector, the moment of the thrust is shifted slightly to the right because the downgoing propeller is on the right side here. So we have the right engine is producing the greatest moment. This means the left engine is our critical engine. Now, what happens regarding the crosswind? And here we need to remember the Weathercock effect, meaning that the aircraft always wants to position its nose towards the wind. So if we have a left turning moment because of the left failed engine, now which wind will give us the greatest left turning moment, which even will amplify this engine created moment? And of course, this will be a left crosswind because now the nose of the aircraft is turning left because of the vector of the thrust from the right engine. And now the wind from the left means that the aircraft nose wants to position itself even more further to the left. This means that left engine failure and left crosswind will be the most adverse conditions in this scenario. Thank you so much for watching. I hope this was helpful. Again, if you have any more questions, feel free to ask. I highly encourage you to get the download the Airhead app and get the account in order for you to be able to see all these questions online and offline and study at your own pace. Again, thank you for watching. I wish you a fantastic day. Bye-bye.